almost 4 years. It's amazing. And before that, the PhD course was in Rano and so on. And now you're the chair of the mechanics engineering chapter, what it's called, at the National Academy of Engineering, and you're on the board of directors for the Texas Academy of Medical Engineering Sciences. And of course, you're known for all of your work on coherent structures, vortices, and so on. And we're happy to have you here, and be interested to hear what you have to say about coherent structures and turbulence interactions.
Thank you, Dan. I'm very happy to be in Sweden after so many years. For the first time, I was delighted a number of times in Landau. Dan's, Arnie's, and Henrik's advisor, a good friend of mine. I feel after Cindy's talk, less nervous about talking about something which has nothing to do with the turbulent long technology, but hopefully there is some commonality. Well, I'm motivated by this problem. This is natural visualization of an airplane coming towards you, got just out of the cloud. The natural flow visualization shows the trailing vortices. You can well imagine if there is a plane following it, especially if it's a smaller one, it could have drastic consequences. So this is an artistic view of a plane flying away and the flow behind it. You see the trailing vortices here. And that's the source of the problem. So in order not to be in the wake of the next plane, you have to wait day or night in busy airports. It's not only during takeoff, in landing also planes go around until they get a chance to land. Which airport? This is probably O'Hare, someone from internet. And but it turns out it is not only during takeoff and landing. Already it's a problem in cruise. Quite often planes suddenly get a big jolt because there is a trailing vortex of plane which has gone by. He cannot see it, but he can feel the jolt. This is about 5 o'clock East time, East Coast time in the United States, and you can see the number of major planes. And of course, 3 hours later, it will be equally crowded at the West Coast. So by 2025, the air traffic capacity is supposed to triple. This is the projection. And you can see this is going to be a big problem. Not only you will have to have triple the number of cars going to the airport and that many passengers being processed, there are socio-political issues associated with that. But there are serious technological questions. And there is another aspect to it. By 2030, we're supposed to have in the United States 20% of the national energy from wind. So there is tremendous pressure to build wind farms. And not too many spaces are available, either offshore or some remote areas, and so you have to pack a lot of windmills. And it's clear that you cannot pack them too close, because the wake of one windmill can impinge on the next, and you'll have very rapid fatigue failure. So you have to optimally locate the windmills, and this study is equally relevant to that. So you can say that the trailing vortex is a very simple practical example of coherent structure, on which I have worked for the last maybe 40 years. And now, from the laboratory point of view, let's look at some prototypical simple flows, like flow out of a hole called circular jet, or a slit called plane jet, flow behind a cylinder in 2D wake or in a mixing layer. In all of this, you can view that the instantaneous flow of a segment of this rolled up vortical structure is like a rectilinear vortex embedded in a shear flow and also fine scale turbulence. So we first studied what is the fate of a little bit of perturbation on a laminar vortex, and we call it core dynamics. And then it's the effect of the linear shear as an approximation on the perturbation on the vortex column. And then the logical step, of course, is to have a rectilinear vortex embedded in fine scale turbulence. And of course, if anybody is looking for a PhD topic, put some shear on top of it. That should be the next problem. This is of interest because, in a conceptual sense, turbulent shear flow can be viewed as a superposition of vortical structures in fine scale turbulence, and this is a generic coherent structure in any turbulent shear flow. So we have idealized this to this problem. Z is the coordinate along the axis, x and y are the radial orthogonal coordinates. This study is done by direct numerical simulation because the intricate details we want to look at cannot be accessed yet with any measurement technique, including holographic velocimetry. The coherent structure is characterized by Reynolds number, which is just circulation divided by viscosity. Computer researchers pretty much limit us to reasonably low Reynolds number. The Reynolds number of the trailing vortices, not 380, but even 747, is of the order of 10 million. So the question is, can you speculate what will happen at these high Reynolds numbers from low Reynolds number simulation? We use Oseen Lamb vortex, which is the viscous version of the Rankine vortex as the basic flow. There are some further idealizations. This is a single structure, so there is no pairing or reconnection. There is no other structure nearby. There is no background shear, so the elliptic instability is not an issue here. The structure is rectilinear, so it sits there. It is curved. The curvature will have self-advection, and the spectral content of the fine scale turbulence is spectrally separate from the coherent structure. The computational method is the pseudo-spectral method for infinite domain developed by Rennick and Lele, and we have used it earlier. So basis it, typically the triply periodic boundary condition used for DNS is okay if you have net circulation equal to 0, because by symmetry the velocity at the boundary has to be 0, therefore circulation has to be 0. This doesn't work well if you have only a single vortex sitting there. And if you do, you automatically introduce some vorticity on opposite side surrounding the main structure, and this causes circulation overshoot. By Rayleigh criterion, such vortex will be intrinsically unstable. So the technique involves finding the velocities induced by the adjacent or image vortices into the domain, and at each time step subtract it out. Details I'm not going to give here. So in this, we start with the identical initial condition. In the traditional periodic boundary condition, you see the vortex undergoes explosive breakup. If you double or triple the domain size, the structure is quite different, always turbulent. So here with the new unbounded domain, with the identical initial condition, flow comes back to the original laminar vortex because rotating flows are very stubborn and the fine scales die down. If you double or triple the boundary domain size, the result is still the same. Another demonstration of this computation scheme is to do a high Reynolds number bending wave perturbation energy growth, for which there is theory available, and you can see that the DNS and theory essentially agree. Almost essentially. Almost identical. So now we come back to the problem we have set out to. There is our vortex or coherent structure, and there is fine scale turbulence. Okay, so embedded in this homogeneous isotropic turbulence is a coherent structure, and we look at the vorticity field in the meridional plane, that is a plane going through the axis of the vortex. As soon as you turn on the flow, the induced velocity of the vortex extends to infinity. So everything is spun around, and there are a lot of threads are formed. Threads means needle-like curved structures. Wherever there was a radial vorticity, because there is a radial variation of the azimuthal velocity.
This is an isotropic turbulence.
Homogeneous and isotropic turbulence, yes. And you see many more threads here, and there are fewer. This means each of them, because of the curvature, advect and meets another one of the same size, they merge to form bigger ones, so you can see a whole bunch of big ones. Now, once the big ones form, so then if they happen to be same way, they will not catch up. But if they happen to be opposite direction, they will hit each other and move out as dipoles, and as you see here, and so that significantly enhances the mixing because of the formation of the dipole.
How strong is the background turbulence compared to the intensity of the wave?
Yes, this is intentionally made very high, 100%, so that the turbulence does not die before the action takes place. So just to accentuate it, the artificially intense Christian turbulence. Inside the vortex, of course, is essentially solid body rotation. There is no strain rate, there is no production mechanism. So dissipation kills the turbulence, and there is nothing left. But these dipoles also, these are opposite vorticity, they cancel each other as they're banging against each other, and they kill each other out.
I'm sorry. What is the length scale of turbulence compared to the length scale of the vortex?
Well, what is it? I think probably of the order of easily over 10:1. But I don't remember the number. This spectrally they are separate in K space. All right. So here is a, of course, systematically doctored, so you can see the coherent structure and the dipoles. You see a lot of pairs, and they kill each other. And after a certain time, only the isolated ones survive. The dipoles have killed each other out. So this background fine scale turbulence is spun around into circular shaped threads. And there is one thing, even though turbulence is killed out, notice there is a semblance of some kind of wavy structure in the core. And that will be the major point of discussion. All right, now we form this thread-like structure. What is the effect of thread-like structure? It transports radially the angular momentum. So initially the circulation distribution as a function of radius is like this. It will transport so that there will be circulation of this form, the circulation overshoot, and this part is associated with a sheet of vorticity of opposite side. Now, imagine a situation where you have a little bit of radial vorticity perturbation. Velocity here is much higher than the velocity here, so it will be spun around into a thread like this. The thread has this kind of rotating motion. So this thread associated rotating motion in the meridional plane will transform any axial vorticity into radial vorticity. Therefore, this closes the cycle. If on the other hand vorticity is negative, it will correspondingly form thread with the vorticity pointed in the opposite direction, and this self-feeding process will progressively accentuate the strength of the threads. Okay, so let's try to understand. So this may be a good way. It is known that if there is a centrifugal instability associated with the circulation overshoot, the Rayleigh criterion flow could be unstable, and therefore this may be a good way to trigger a transition of the trailing vortex, so the next aeroplane doesn't have to be 8 miles away. It can be a lot closer, and solve the problem of building more runways, which is not very likely for airports like San Francisco or O'Hare. And so this is the goal. Is there any way we can come up with a technique by which we can break up the vortex? So here is an artificially generated circulation overshoot, about 15%, which is a little bit too high, just to emphasize the mechanism. And you see immediately it forms some kind of a thread-like structure, and they form dipoles. They radially advect out. The corresponding, this is the vorticity cross-section, this is the vorticity surface. So you can see there are many dipoles, and they're associated. And after a while, these dipoles kill each other, so the vortex reverses back to the original vortex. So it doesn't look like the centrifugal instability is a likely way to develop method of transition of the vortex, because it's inherently self-limiting. Now let's look a little bit at the vortex structure. The corresponding azimuthal mean velocity as a function of radius up to 500 turnover times is pretty much same. Of course, the radius is increasing, so you scale back. So essentially, it's like that of a laminar flow, even though the turbulence intensity is indeed very high, almost 10%, and it has not decayed that significantly. But turbulence seems to have very little effect on the rotating flow, which is pretty well known. So we then have to look for some other possible mechanisms by which we can have more rapid decay of the trailing vortex. So let's look a little bit at the dynamics of this vortex column in the presence of this fine scale turbulence which form threads. So what we did, we carried out the same simulation 20 different times, as if you took data for 20 different successive time windows, and then ensemble average. This is the radial velocity fluctuation intensity, this is azimuthal, and this is axial, and this is the Reynolds stress. There are two surprises here. One is Reynolds stress and the radial perturbation has a peak outside the vortex, just at the boundary. And second, in spite of the fact that it has essentially relinearized, the fluctuation intensity is very high, and even higher than the imposed turbulence fluctuation. And these two mysteries we'll try to explain. It is mystery because even though Reynolds stress has large excursions associated with the phase at which you happen to capture it, the average is essentially zero. So there is no production mechanism, yet fluctuation is very high. And it turns out this is connected with the wavy structure we saw earlier.
It depends on the perturbation you put in as well, right?
No, I mean, no. It's just vortex in fine scale turbulence, that's all it is.
Right. Okay.
And
That's what I mean.
the perturbation is homogeneous isotropic.
It's
Spectrally
scale,
separate.
it's intensity, etc.
Yes. Now, let's look a little bit about what's happening. Here is the core size. This is the vortex column. You put a radially much larger extent of fine scale turbulence, and you see with time two peaks develop, and the peak in the central line exceeds that of the post turbulence. Now let's say, well, let's put turbulence only inside. The turbulence just decays because there is no production mechanism and becomes laminar. If you mask the turbulence so that it's only outside the vortex core, it does indeed produce similar turbulence distribution. So there is some funny mechanism by which turbulence outside the column can talk and induce turbulence or fluctuation within the column. And at this very moderate Reynolds number, as you increase the Reynolds number, the central line intensity increases. So at the practical Reynolds number, not at 8,000 but 10 million, perhaps the intensity will be so high that it may break up the vortex. So there are three possible mechanisms we can think of. One is centrifugal instability, which is the first obvious choice, and we found that self-limiting is not very promising. Second, can we have this thread and wave within the vortex somehow resonate? So here we consider to idealize the threads we form rings around, they're all in the same sign. So if you consider three adjacent rings, consider the one in the middle. This one will induce a positive velocity along the axis and radially inward. This will produce radially outward. They'll cancel each other. This will add up twice. So apart from the self-induced motion of a ring, they'll also have mutual induction, and there will be a third effect because of the image vortex of this inside the column. So as a result of this, these vortex rings will advect. In this case, of course, it's to the left. Now suppose in the frame, and there is also core waves, I call core dynamics. And if the self-advection of the ring associated with the three effects, the propagation speed exactly matches the core waves, then in the frame of the ring, the perturbation is continuously added to the core, and you may have core resonance. And indeed, that's what happens. So how do you carry out the calculation? You have to choose some wavelength. This is the actual wavelength. So these are the speed of the ring advection at different relative strength of the ring. Gamma means the ratio of the circulation of the ring to the circulation of the column. That means this circulation divided by the column circulation. And you know, as you go higher, the propagation speed increases, and these are the corresponding number of eigenmodes of the core waves in the column. So it is at the intersection where you choose so that you can get the resonance condition. This is how you carry out the
Where is
calculation.
the radius of the core here? Where would it be? And how big is the radius in that?
Oh, this is not given here. That is, here you can see, but I don't remember. It's probably going to be, this is the starting diameter of the column, and this is the diameter of the column. So this is the realistic situation. So this is the case where the circulation of the ring going around, this is the meridional flow, the circulation is 10% of the column circulation. And immediately, as you see, of course, the vortex diffuses with time, increasing time, and immediately you see the perturbation in the core, omega z and omega r. The perturbation, I think, is kind of maximum here, and then it dies because this is, remember, a row of vortex rings. They diffuse, run into each other, and form a sheath of vorticity. And when the sheath is formed, the associated radial perturbation necessary to induce the perturbation in the core is not there anymore, and the perturbation slowly dies due to viscous dissipation. So there is a range of growth up to this time, and then it decays. Correspondingly, if we look at the actual vorticity perturbation at a half wavelength apart, you see the perturbation is exactly out of phase. It grows up to this time, then it decays by the mechanism I showed. And for this, the resonating wavelength is very important. It's not just the circulation of the ring. Even a stronger ring, if they are not at the resonating axial wavelength, may not grow as much as even a weaker ring at the resonant wavelength. Now this is interesting to show that as a function of Reynolds number, the growth can be, it increases with increasing Reynolds number and lasts longer. You see, it grows and then decays, and it continues to grow up to here. So again, at practical Reynolds number of 10 million, perhaps this growth will be enough to break up the vortex. All right. So we see that we get growth, but it doesn't have indefinite growth. So perhaps it is a little bit more promising than the centrifugal instability, but not as promising. So perhaps we should look into transient growth. And this is a characteristic of the perturbation of operator, which is non-self-adjoint. Here I give an example from Dan's book, that if you have two matrices, they have, these are the two eigenvectors, they are not orthogonal, and therefore, and both of them are decaying. And now imagine this are the two modes. This decays much faster than this. So at this instant, this will be the resultant as the hypotenuse of this parallelogram. Little bit later, this has decayed quite a bit more than the other one. So that will be the two corresponding amplitudes. But you see, this is the resultant, and eventually, of course, this decays, so the resultant latches on the list decaying more. So you see, the resultant shows a temporary growth before decay, and this is what we call transient growth. So this is known. The question is, how does it happen physically? It turns out some years back, Steve Davis, you all know, was visiting me and challenging me to show what is the physical mechanism. So he showed that in a bound layer, that's a paper by Schopper, and here we'll talk about transient growth in the vortex column. So what are the mechanisms involved? So there is a two-dimensional mechanism and three-dimensional, two mechanisms. One is based on strain, another based on force. So if you consider the energy associated with the perturbation, the stress times the strain rate, turns out for this flow, if you're looking at outside the vortex core, the strain is negative, therefore this is negative, for perturbation to grow, UV must also be positive. So let's consider outside the vortex core a perturbation streamline. So where the tangential component increases with the increasing theta, and so on any of this line, either both U, the radial component is positive, tangential component is positive, so product is Reynolds stress is positive, or Reynolds stress is positive because both of them are negative. So this is a positive tilt perturbation streamline, this is negative tilt perturbation. I mean, both are positive tilt because the radius increases with increase theta. Now, near the vortex, speed is much faster than away. So you can see after a while it will spun around so that this curvature will change the other way like this. And now you see UV product is negative, so what was initially unstable will turn into a decaying mode. So this is a two-dimensional mechanism. It's purely shearing. There is no vortex stretching into it whatsoever.
Why does it change with time? Sorry, the tilt.
Okay, just imagine there is a line. So this is at a lower radius, so it moves faster than this point.
Oh, I see.
So it just turns around that way. Now, the three-dimensional mechanism, you can have a radial vortex filament, and again this C will move faster than D, so immediately it will spun around in the azimuthal mode, and in the corresponding situation, sometime later it will look like exactly the ring around, and they're associated with this, both U and V are either positive or negative. Again, this is a destabilizing configuration. So, you can decompose a flow into mean vorticity and mean strain. These are in the field outside the core where there is only mean strain, there is no vorticity. And we have shown why it is destabilizing. Let's look at what is happening when there is vorticity, namely within the core. So in order to do that, we have to understand core dynamics. Rather unimpressive event that we just give a sinusoidal perturbation to a rectilinear vortex what has this. Turns out it's a very rich dynamics. This is published in 94. So imagine this is a vortex column and you give a sinusoidal perturbation, so that means on the surface circulation is constant. Since radius is more, azimuthal velocity here will be less and here will be more. So in the meridional plane you have sinusoidal vortex lines. This is spinning faster than this, so vortex lines will take this form. Associated with this coil vortex line, there will be meridional flow. If you put your right hand side, you will see how the flow goes around. And so the meridional flow will oppose the cause for which it is created. Namely, the radius was more here, now the meridional flow has the pattern, so they will push this one in and that one out. So when the flow becomes rectilinear again because of this motion, it turns out the meridional flow is maximum. So therefore it will overshoot. So where it was, it will be just the opposite. So you can see therefore the vorticity perturbation difference half wavelength apart will undergo sinusoidal oscillation. The Reynolds stress will undergo oscillation at twice the frequency. And because of the oscillation of the Reynolds stress, the energy growth will not be indefinite as was in the first case, but it will go through cyclic oscillation.
The Reynolds stress is twice the frequency because U and V are opposite or something.
Well, you can see here, yeah, because U reverses, but half period apart, it is the sign is same, the product. Okay, so let's cook up an artificial flow which consists of a vertical part and a straight part. Alpha is a measure of strength and beta is a measure of vorticity. Consider the case where initially there is no vorticity, purely straining motion, and we can show that the perturbations grow linearly with time, therefore kinetic energy goes infinity. Turn on a little bit of vorticity, then the growth is arrested and it undergoes oscillation. With increasing vorticity, that means increasing circulation, the growth is arrested earlier and the oscillation also happens.
This V here is for your perturbation or for your...
This is the beam flow. So you can vary alpha and beta to get relative amounts of. Okay. So far we talked about linear, inviscid, transient growth. We have not yet come to nonlinearity. Strain produces unbounded growth of perturbation kinetic energy. The moment you get in any vorticity, it arrests the growth and introduces periodic oscillation. This is inviscid. If you add viscosity instead of just oscillating, it will also be slowly decay. All right. Now this is the optimal mode and the maximum gain. I will not get into those. We split into axisymmetric and bending modes. You can see that the gain, even at this moderate Reynolds numbers, can be rather large, 2 to 3 order of magnitude more. And now the question is, which one of these two modes is more likely? So start with a very small perturbation. Here it is 100 times. So actually it's 100th perturbation. You can see that indeed the bending mode is much more dangerous, or in our case more preferable, because the growth is much more and it remains in the axis, and whereas in the case of the axisymmetric mode, the growth is much less. So we try to then focus only on the bending wave mode. The corresponding radial perturbation vorticity. Remember, radial perturbation vorticity is a measure of growth, because radial perturbation vorticity is turned by the strain into the azimuthal, and then that has both positive Reynolds stress. So in the case of, this is the axisymmetric mode, as you increase the Reynolds number, the perturbation vorticity decreases. And here it continuously increases. Second, it moves away from the peak strain rate. So it is the radial vorticity times the strain rate that gives production. So it will also continuously decrease because it's moving away. First it is decreasing itself, second moving away into lower and lower strain rate. In the case of bending wave mode, it remains pretty much near maximum strain rate and progressively increases with increasing velocity. So we have to worry or be excited about the bending wave mode. Question is, how does this bending wave mode grow? Now, bending wave mode means...
What is M now?
M is the azimuthal wave number.
And why is M equal to 1, the bending wave mode?
Well, M theta, so M is equal to 0 is axisymmetric, M is equal to 1 is bending.
Oh, that's what you call bending.
Yes.
I see.
So, M is equal to 1, or bending means the perturbation vorticity across should be in the same direction. That's okay. Now, as this core goes around, it will tilt this perturbation, the radial component into the azimuthal direction. So pretty soon it will be like this. Now it is interesting because both of them induce radial velocity one way, so they are cumulative, and opposite way across their line of connection. And same thing if you rotate here, this diagram is same as this, so that we retain the same coordinates. And indeed you can see that the maximum vorticity, which is in the axis, will be tilted towards the radial direction. This radial vorticity perturbation now has associated with another velocity gradient, and that will tilt this axial vorticity in the orthogonal direction. So this plus this together will form a radial perturbation vorticity, which will be spinning around depending on the radius where the perturbation is introduced and the associated velocity induced by the core. Now, inside there is also bending core wave mode. So if these are because of the there is a large number of axiomatic and bending wave modes within the core. These are so-called Kelvin waves. Now, if the rate of rotation of the internal Kelvin wave and the rate of rotation depending on the radius of perturbation are same, then this bending wave mode will be continuously energized and there will be resonance. This resonance is different from the resonance I talked about. Intensity occurs, and I'm not going to focus on that.
The velocity gradient you see, one of them is internal to the vortex structure. Is that right?
Yes. All right. So now, let's talk about nonlinear transient growth. What happens if the amplitude is large? So if case A is linear at 10 to the minus 10 and progressively higher amplitude is the most nonlinear and the corresponding perturbation energy grows as a function of time. Now, if you look at the cross section of the column, the vorticity distribution, the linear one remains same, the eigenfunction doesn't change. People always worry about when is it nonlinear. When you see the eigenfunction has noticeably changed, that's the beginning of nonlinearity. And you see the most nonlinear case looks pretty contorted. Of course, the Nernst number is low. So it seems like with increasing Nernst number, the core will be contorted enough to probably break up and form large-scale turbulence out of the core. Now consider this case, the one which has the maximum growth for 6% initial perturbation. And this is the time where we had the previous picture. But even though this is the time of maximum perturbation energy is decaying, but the core gets much more interrupted and more turbulence-like. This is the corresponding structure outside and the core shown as vorticity surface. Okay. Now let's do it at different Reynolds numbers. You can see for this bending wave mode, as we increase the Reynolds number, the core gets, by the way, light means vorticity on one side and dark means vorticity on the opposite side. So it seems to be much more contorted with increasing Reynolds number, and also the contortion lasts for a longer time. So perhaps at very high Reynolds number, it will break out into.
So these are all full-scale simulations in a closed periodic box or something?
Period, it's not, it's unbounded or infinite domain, done in a periodic box, but at each time step, you subtract out the effect of all the periodic adjacent boxes. Equivalently, it is infinite domain. Now, there's something else I'll just hint at, and we have also explanation. So, this is the perturbation, normalized by initial perturbation, as a function of time. So, as you increase the Reynolds number, there seems to be a resurgence of the perturbation energy, and indeed there may be a second transient growth. So, Kosu was saying that he has already talked about a secondary transient growth. It may or may not be, because mechanism I think is different, but I have not studied secondary transient growth, so I don't know. So this amplitude is actually much larger than this because it's normalized by initial amplitude. So you can see that this is a linear case just goes to uneventful decay. In the nonlinear amplitude of perturbation, it decays and then again picks up. And I will not get into Now, the regenerative transient growth, here is a case. You see it has broken up, turbulence like, and number of contours gives an indication of how strong the structures are. And you see it has decayed down quite a bit and then picks up again.
Sorry, could you remind us what kind of perturbation you have on this? What kind of perturbation it corresponds to?
This is the optimal mode you determine and then you put in as a starting point. Alright, so that's pretty much all I've said. Am I in time? So, external turbulence can induce core fluctuations leading to large amplification. Even it's larger than the external perturbation. And we explore several potential mechanisms of core transition. Centrifugal instability is one possibility. It turns out it cannot be exploited to cause rapid large growth of the perturbation because it's self-limiting. The second, even weak threads can cause large perturbation in the core by resonance mechanism, but again it does not, it has eventual limit and then decays. But it's clear that transient growth can give orders of magnitude amplification, and strongest of the transient mode is the bending one. And these are possible further research topics. Thank you.
Thank you. Any questions?
So what's the, when you were, as a result of all this study, what is the best way to wake up the data? That's very good.
Well, I didn't get into the technological aspect. You have to keep the right perturbation, the right radius. Either mechanically at the aircraft wingtip, you put some rotating perturbation or some acoustic device by which you can induce. So maybe instead of, as I say, 8 miles, maybe 1 mile, you can have the next airplane. And it may indeed be able to cause the breakup. So that requires some full-scale testing. So far we haven't found anyone willing to do it.
I have a question too.
Yeah.
With these vortex pairs behind airplanes, if you think about that application, or actually multiple vortex pairs across it, depending on how the flaps and things are.
Yeah, this has been suggested by others.
Yeah, but my question is that there's also instabilities associated not with just one vortex, but with the vortex system, and the wind null instability, and then you get crouch and those guys who work there.
Yes.
So, and that's quite unstable, I think. But how is this related? Is this much more unstable, or is it better to induce these instabilities than to
Well,
induce,
Jeff Crouch and Honora people in France, so far I don't think they have come up with any
okay.
positive solution, even a possibility, so they're trying very hard. Their idea is not so different conceptually. Instead of having 2 wingtip vortices, they have multiple flaps, so you have a lot of little vortices. And potentially you can diffuse them enough, but so far they have not been successful. I think this is quite promising. I think some acoustic devices could be put at the wingtip. It may have some drag penalty, but eventual benefit will far outweigh.
What are the scales of these instabilities compared to the, let's say, the wind null instability? Or
Crow instability is something. Crow instability is a much longer wavelength.
Right.
And I think this is like in a few, maybe of the order of the plane length.
Right.
This is what will work. Whereas crow instability goes way far downstream.
What about regional instability? So you could induce some instability.
You mean electric? I have not explored that.
That too must extract energy from the vortex.
Sorry?
That regional instability could also extract,
Yeah, I think so, yeah.
extract energy from the.
Yeah, I have not explored that, but I haven't seen us talk about. It's a must to explore that.
Okay.
Actually, I said I must clarify, as in science, this we have been studying for a long time. This trailing vortex, I was in a US national panel only last year. And then I see, oh, there is probably an application to what we do. But the core dynamics we have been studying for a much longer.
That explains the introductory transparencies.
Okay, any other questions? Okay, well, let's thank Vasily again. Thank you very much. Okay, now we have Andrea Gruber.
So, hello, my name is Andrea Gruber. Perhaps some of you were waiting for a young German girl. I'm an Italian man. Okay, today I will talk about flames in boundary layers. This, I think, is a good shift, being one of the last talks of today, as next week the program on combustion will start in the same place. So it's a good switchover. What we see here is a flame propagating a boundary layer, picture from above. So the channel wall is this one, and we have a flame propagating that direction. This is a very nice new work that is being going on at Technical University. So I'm from SINTEF, and my collaborators are from, well, you can read by yourself, the three continents. A little bit of background. So turbulent combustion happens mostly in enclosed device, as engines and gas turbine combustors and furnaces. So here I show a gas turbine combustor from Alstom. Is the EV burner, as they call it. So there is a swirling flow of air, and there is some gas or fuel injection holes along the wall. Forget about liquid fuel, it's not on all the time. And the flame in premix mode stabilizes outside the sudden expansion. The problem starts when the flame decides, because of some problems in the process, to creep into the combustor. So in that case we have what is called flashback. And combustion in boundary layers is also connected to something called the unburned hydrocarbons generation in automobile engines. Now, turbulent combustion in itself as a research field is quite mature, as it is turbulence research. I believe that the combination of combustion research and turbulence research are not so mature, and models like these ones are really giving poor results most of the times in boundary layers, when you have flame in boundary layers. So also experiments, you know this very well, experiments in boundary layers due to the small sizes are very difficult, especially when you have a flame and when your laser sheet has to have a lot of power to visualize the radical. So I will talk today about two topics. Mostly they happen when a flame which is located outside the burner flashes back into the premixer, and there are several mechanisms of flashback. not all of them include boundary layers, but there is one in which the flame creeps along the wall. Also, once the flame has got into here and it gets close to the injection, to the fuel injection hole, you want to design your combustor so that when the transient that brought the flame inside is gone, the flame is automatically washed out. That is, intrinsic flashback safety implies no flame holding, so that the flame does not stay here near the injection holes when the transient is gone. So we don't want to have flame holding here, and therefore we are trying to understand how this flame holding happens. So this is one topic. So acquire detailed understanding of flame propagation in boundary layers and of fuel injection and flame anchoring are the key challenges, especially when you look at new fuels like hydrogen-rich fuels, because hydrogen has property, very reactive combustion property. So today I will show you some overview. I removed from the presentation a lot of stuff regarding chemical kinetics because I don't think this is the right how to do attendance for that. I will show an overview of two simulations, one in a channel flow, the other one in a boundary layer with the jet, a transverse jet, with a flame attached to it. So in this case we have a premix, so the fuel, you can see here the turbulence represented by the multisig magnitude. You have premix reactants here, a flame anchor that holds the flame in place, and a flame surface that wipes out the turbulence mostly. This is because of the temperature jump and increase in viscosity. In this case, there is a non-premixed flame because the air comes in the direction of the cross flow and the fuel comes from the jet. So they mix here in this region. So both cases are run at Oak Ridge National Lab using the S3D code. Few details about the code is a compressible formulation. This we have that you don't care about, usually. So we have to find the reaction rate for all species that we want to transport. For hydrogen, in the case that I'm simulating, there are 9 species and 19 reactions that determine the reaction rate for all species. So I have 9 transport equations here.
This does not include all the transient reactions and so on.
Yeah, these are all reactions that describe the system. So S3D has an 8-order finite difference discretization in space, third order at the boundary because we use one-sided stencils, and high order temporal integrator. So the channel case, we have the old Kim, Moyne, and Moser Reynolds number with preheated reactants. So we have heated them up at gas turbine condition. This is not gas turbine condition, obviously it's atmospheric pressure, but increasing the pressure means decreasing flame thickness and very high requirements for the DNS. So the inflow boundary condition here are generated in an auxiliary simulation of the Kim-Moyne and Moser channel. So there is another simulation that does only the channel, and then we sample at one YC plane and put the fluctuations here, so that we have the correct turbulent inlet. The flame is initialized as a V flame here behind the rod, which is a numerical anchor. We impose burn conditions at the rod. So this is the resolution that we have used. mostly because of the flame, which is thin. So here another snapshot. You may see the black line, which is the flame, and some of the turbulent structures of the boundary layer that are going through the flame and disappearing because of the temperature increase. This is another snapshot.
So how do you define the flame here?
Yes, I will come to that in the next slide. You can see that the flame in the middle of the channel is mostly not very wrinkled. It's like a planar flame, but in the further down in the boundary layer it gets very wrinkled. So now to your question, we define in combustion usually a progress variable C, which is 0 in the fresh reactants and here. So the surface you saw before was the progress variable at 0.7. One observation here, you can see that the flame brush, or the average thickness of the flame, it increases when going to the wall. Now, this could be the effect of the flame flapping, but also the flame thickening in itself. And I will show that it's probably a combination of both. So, if we take a laminar flame and we take the gradient of the progress variable, we get that a thinner flame for a high equivalence ratio has a higher gradient than a thicker flame at lower equivalence ratio. So the gradient of C gives us an indication of the flame thickness. The probability density function of the gradient of C show us that for the last position there is a dramatic change in decrease in the gradient of C, so there is an increase of the flame thickness towards the wall. This is because of the cooling. The wall is kept at temperature of 750 K, so there is a heat loss. Also, another average picture showing the reaction rate of the fuel that disappear at the wall, sometime above 12, Y plus 12. I'm sorry for this, obviously this is 0, and 180. So the fuel reaction is absent in the wall because of quenching. Another indication is that the flame displacement speed, SD, is nearly equal the laminar flame speed for this flame, but going towards the wall it decreases, but does not become 0. The displacement speed of the flame surface has several components. One of them is the reaction rate, so that goes to 0, but the other components, like diffusive part, contribute to the non-zero displacement speed. Also, looking at the averaged wall heat flux, you see a peak at a certain distance from the inlet. It peaks at 1083 wall units below downstream the exit. So this is the position where the average wall heat flux is peaking. You see an instantaneous picture of the wall heat flux. This is the profile of the wall heat flux span-wise. You see there are large variations. This is 2 megawatt per square meter. Okay. So radiation, if important, it is not for hydrogen flames, but for other flames it is, would eventually smooth this steep peaks. So now, well, I will not try to compete with you in representing wall structures. So I will. I'm just trying to visualize some of them by showing the wall normal verticity at y plus 5. I can see some elongated structures that will move towards the flame, and what we see with the colors is the wall heat So when they come, when these structures come here, they induce a kind of hotspot, or, well, a lot of heat flux. Again, the boundary layer is modified by expansion and acceleration, so it is not so easy, I believe, to identify the structures and see how they are stretched and accelerated. But so our approach was very.
This is an isothermal one in the center, right?
Yes, it's an isothermal. So what we did is just to sample in time. You see, this is the time direction. This is the span-wise direction. Somebody today talked about a similar approach. We sample in time along this maximum average wall heat flux line. And then we did the spectral analysis of this data, and we found that this peak in the spatial frequency is 100 viscous lengths, and there is a kind of plateau between 80 and 200. Also, the time spectrum has a. I marked the position of an outer scale, but it has a plateau between 10 and 30 wall time units. So now I don't know how long on average these structures are. I hear from you that they vary between some of these numbers. In this case, they will probably be elongated by the acceleration. Also, they move at a speed which is changing in the domain. It's not constant because of the acceleration. So it's probably something like that. Doing order of magnitude analysis, we can see that this, if they have such a turnover time, then they will have probably a typical streamwise structure passage time, which would then be in accordance with the time spectrum. But this is not obviously proof; it's just the indication that they may have something to do with that. So, just 4 slides about this. We have a boundary layer with cross flow of air and hydrogen. The cross flow has 55 meters per second, same temperature. The boundary layer thickness as given. The jet has a Reynolds number of 2,700, so it's basically laminar. We consider it laminar. This case is rather big. It was run on Jaguar for about 4 million CPU hours at Oak Ridge. This is the resolution, spatial resolution. And the aim of this was to understand the flame anchoring mechanism. If the flame anchoring is connected somehow to the boundary layer or it's above it. So we see some noise coming from the vortex shedding and from the flame attachment region. And the sound waves will leave the domain through this boundary formulation. A time analysis of the flame will show that the flame preferably seems to anchor in the vortex shedding that is happening downstream of the jet. This is 2 microseconds difference between these frames. And it does not seem to be connected to a low velocity region here. So this is the average velocity. You see that there is a low velocity region here where these black lines are the heat release rate, average heat release rate. And the low velocity region here is not touched almost by the flame. So we can say that the boundary layer in this case has very little to do with the flame anchoring. this is ongoing, and I will not be able to show much more than this. We are using the PQR flow topology to try to identify the most upstream flame location and its coupling with some of the flow structures. But this is ongoing, and I have not so many slides. So.
Why is the PQR topology the right thing to do?
Well, this configuration is there is a very complex flow field, and I'm not sure that other. Well, okay, let's put it like this. If you have better ideas, please tell us. The animation shows the simulation with the flame tongues always entering the vortex schedule. So, this I already commented about the flame wall interaction. There seems to be a connection between the near wall structures and the heat wall, voltage flux spectra. Flame holding seems to be related to the vortex schedule and not to the boundary layer. These are some ideas for the future. Among others, we are going to investigate the effect of the boundary layer turbulence, so different kind of thickness of boundary layer and so on, of the nozzle shape, of the injection angle, and on flame holding downstream of the jet. That was it.
Thank you very much. Time for a quick question before a couple of them.
You may have said this and I missed it. What kind of input profile do you impose to start the test in the wall? Is the pipe model or
No,
it
is not. It is
top gas or parabolic?
It's a parabolic profile because we assume that the pipe flow has the lamina. So parabolic profile. We know that for lower velocity ratios there will be some entrainment of the cross flow field, but not for such high velocity ratios. So there will be perhaps a slight asymmetry due to the pressure field, but very marginal.
I would like to have a few details concerning the solutions. How many points you typically have inside the flame thickness first? And second, which is the characteristic ratio between the dimensions of the turbulent structures and the flame thickness, especially close to the wall, when you say that the flame tends to broaden?
Okay, the double color number close to the wall. Which case are you referring to?
Oh, the one for the channel.
Okay, the double color number at the wall was about 0.26. So that gives you an indication. For the resolution, you were meaning
how many points you get inside the
for the same
for the same kind
for the channel.
Okay,
it's about between 5. It depends where, but and also on the inclination. It has
as in order
between 10 and 5.
Okay, I think we have to end it there. Thank you very much. We have come to the last talk given by Hein Schaal, and it's about visualization tool for launch turbulence simulations, and you said you would introduce yourself.
Well, I guess the story behind this is that so I met Johan. Let's see, you said it was August of 2008. Is that right? It was sometime in the summer of 2008. We were both visiting Argonne Labs, and so I said, Visit is a good tool for this, and Paul Fisher, who we both collaborated with, said yes, use Visit, and we exchanged an email last week, and I told Johan, I'll be in Stockholm, on Friday. I'm going out to Norrköping to give a talk on visualization. He said, you should come and tell people about Visit here. So here I am to talk a little bit about Visit. And I saw Andrea gave a Visit movie as well.
Yes.
Yeah, so,
I used the same movie.
Yeah. Okay. So excellent. So anyway, I could get up and just talk about the product, but I thought that maybe I would start by talking about some success we've had in the turbulence space, and then I would give kind of an overview of the project afterwards. So let's see. So this was a simulation that was run 4 years ago when the Livermore BGL machine was kind of the biggest machine in the world. It was a 3K cube data set, a rarely Taylor instability, so a heavy fluid on top and a light fluid on the bottom. And then we're looking at the mix mixing region here. We've removed the pure heavy fluid, the pure light fluid, and we're looking at just the mixing region in between. And so the reason I'm here, and the reason that I think you all might be interested in visit, is if you have large data sets, and many turbulent simulations do, you have to do something special. And so to make this image, I took a program that was a distributed memory parallel program that did the I/O in parallel, that did the processing in parallel, and did the rendering in parallel. And so the product that I'm telling you about does this.
This is various folks.
This is an excellent question. I'm a CS guy. I'm going to totally embarrass myself to get into the details of turbulence. So I'm actually pleased that I understand the really tailored instability. This one's a DNS. The next slide I know even less about it, but I can tell you all about the viz. So okay. So here's the next one. This is another DNS high Reynolds number simulation. I don't know too much beyond it. This is a 4K cubed data set that was run recently on the University of Texas Austin's Longhorn machine. And so for this simulation, they were interested in areas of high entropy. And so we went and identified connected components. And so you can see these high volume connected components all throughout here. And in fact, they're actually kind of hard to find. Here is just an isosurface of high entropy. And then here is a single component. You can actually see the single component if you look at the blue there and the blue there. That's buried among all these small components. And so to actually go and be able to detect these large components and isolate them and show them is hard. And it's really hard in a distributed memory parallel setting. Because if you're parallelizing over the data, this processor may own this chunk and says, well, this is a component, but this processor may own a different chunk. And these two components it thinks are different because it doesn't know about this horseshoe path. And so you have to do, it's not terribly hard, but it's a tremendous bookkeeping problem to be able to do this in a distributed memory parallel setting, to be able to come back and identify which components are actually connected and which ones are not. And we can do that and be able to do analysis where we go and identify components like this and be able to track them over time. Okay, so here's the last example in the turbulent space. Gosh, this image didn't turn out as well here as it did on my screen. So this is a NEC simulation run by Paul Fisher and Alex Ababko at Argonne. The idea here is we have a nuclear reactor. There are 217 pins, and they're actually modeling the water that goes around the pins and are cooling the pins. And the idea is, what you want is you want the water to circulate a lot. If you have a hot pin right here, and as the water that's being pumped in from this direction down the z-axis, if the water is circulating a lot, well, then that means cool water is getting in to cool off the hot pin. If it's not circulating a lot, then you've got the same water that's getting heated up and just sticking around that hot pin. And so a really important question is, how much circulation is there of the water inside the reactor? And so in 1970, they actually did an experiment like this. They break this region down into channels. And so each pin goes around one of these little vertices. And each one of these channels is one of the numbers there. And they took a whole bunch of dye and placed it in a channel, and then they went to the backside of the reactor and measured where the dye came out, and they got a sense of how much mixing there was. And so now, Paul and Alex have run this simulation, and they want to understand, well, does their simulation get the same results as the experiment? And so, if you think about it, what you can do is you can just take a particle, put a particle into one of the channel locations, and infect the particle based on the velocity position, and then measure where the channels are. So here it started in this cyan channel, blue channel, salmon channel, green channel, eggplant channel, and so on. And this view is just looking at the particle direction as it goes down the z-axis. And so if you do this for a single particle, you have a sense of where the dye is going. And if you do it for like 1,000 particles, or maybe 10,000 or 100,000 particles, you can actually start doing statistics on this and actually go and do some co-validation where you're matching up what the simulation is doing against what the experiment is doing. And so you can place 1,000 particles in the channel, and then you can measure where they come out on the other end, and you can compare that with the experiment. And so the theme of my early examples here is that to do analysis like this, you need to have a good visualization tool that knows how to handle large data and knows how to do all these algorithms in a pretty sophisticated way. And so playing to that theme, this is actually a really hard thing to do, right? If you want to do parallel particle injection, there's kind of two classic strategies. One strategy is to parallelize over the data, but that introduces terrible load balancing issues. Another strategy is to parallelize over the particles, but if you parallelize over the particles, you have lots of problems with redundant I/O. And so this product I'm going to tell you about, Visit, actually has a best-in-class algorithm that we demonstrated at SCO9 that balances between these extremes. So these were kind of 3 examples of success stories in the turbulent space, all of them kind of focusing on why you need to have smart, large data infrastructure just to handle the scale of at least what I've seen in the turbulent space.
So the particle is vector at each step by the local velocity difference, something like that.
Yeah, we got it. So, run to kata, what else do we have? We have Adams Bashford, run to kata, we have one more escape. Okay, so what is Visit? Visit is an open source tool. We kind of have 2 focal points. One focal point is large data. The other focal point is that we have an end user tool that we can hand out to folks. And so, there's a lot of research that goes into the tool, but it's something you can download and use, and you don't need some graduate student sitting next to you to help you use the tool. And so if you think about having a large data focus and having a usability focus, that's a pretty good niche for the supercomputing space. So it's used by a diverse set of people. So Viz experts, yes, but simulation code developers probably make up the majority of our user base. And then people that run simulation codes, engineers and physicists also are users of the product. Very popular, more than 100,000 downloads on the web, won an R&D 100 award in 2005, and it's used kind of heavily to exclusively on 8 of the world's top 12 supercomputers. Okay, so it's terribly named. It's terribly named for 2 reasons. Number one, if you Google Visit, you'll find like Visit the Bahamas. It's impossible to find, so you have to Google like Visit visualization to find it. But it's terribly named because it kind of mentally pigeonholes you into thinking about a tool that does just visualization. And we think about the tool doing more than that. We think about being built around 5 use cases. And so one of the 5 use cases is debugging. It's the dirty secret of the visualization business that people use our products to debug their simulation codes more often than anything else. And so we have a lot of functionality in the debugging space. Quantitative analysis, comparative analysis, so simulation to simulation, simulation to experiment, and then 2 classic visualization type use cases. So data exploration, here are pictures of slicing, contouring, volume rendering, and presentations, making movies, images for PowerPoint, etc. And so we think about the tool being about all 5 of these use cases. And so Visit is a good name for the top 2, but it's not a good name for the bottom ones over here. When it comes to quantitative analysis, when you talk to a Viz guy like myself, definitions of quantitative analysis vary. It could be something as simple as integrating density to find a mass. It could be something as complicated as adding a synthetic diagnostic to reproduce your experiment so you can do a simulation to experiment comparison. And so we think about Visit doing everything in that spectrum.
Question? What platforms does it run?
Yeah, great question. I've got it on a later slide, but Mac, Windows, Linux, supercomputing, OSs, so AIX, all the powerful ones. So let's see. So we have a really rich feature set. Support lots of different mesh types. So data types, scalars, vectors, tensors, materials, species. Obviously 1D, 2D, 3D time varying. Lots of different ways to render your data. Lots of ways to manipulate your data or down select what you want to look at. That should be updated. We have over 100 file format readers. We have good support for derived quantities, so ways to make, we call them expressions, new fields that are combinations of existing fields. All the general features you expect in a visualization tool, position lights, making movies, etc. And then the real secrets are in the queries. This is the way you pull out the quantitative information, do the debugging, do comparative analysis, and so on. So there's a lot of functionality in this tool. It's applicable to a lot of different science areas. Okay, so this is a slide that says we know how to do parallel viz pretty well. The idea is we have a client-server design. You don't have to run client-server, but if you've gone off and done a simulation at one of the big supercomputing centers, you would leave the data at that center. Andrea was talking about running at Oak Ridge. My guess is you're running a client on your local desktop. You're connecting to the Oak Ridge Jaguar machine. You're doing viz in parallel on Jaguar and shipping images back. And I think that's probably the right way to go because moving data.
Yeah, you can't move.
You can't move data. It's a tremendous pain, exactly. And so the idea then is we process data in parallel. You read in, if it's 3-dimensional data, volumetric data, you apply visualization algorithms, for example, a contour. It produces a surface. If the surface is small enough to transfer back to your local desktop, then it would transfer to your local desktop and render it interactively using your graphics hardware. Often, if you're starting with, for example, the scale that you guys have in the turbulence community, that surface is going to be so large that it will overwhelm a single GPU on your local desktop. So you have to have a backup plan. And the backup plan is that you leave the surface on the remote machine and you do your rendering in parallel and send images over the network, and that's actually quite a good strategy and works pretty well. So this is kind of our strategy for dealing with large data, and we found it to be very effective today. Okay, so here's a slide where we say that we're really committed to making a robust product. So we have manuals. The manuals are a little bit out of date, but we're working on it. We have good support for users, wikis, mailing lists, and so on. We do all the things that you would expect for a team that wants to deploy a tool that's usable, revision control, like regression testing. Here's the response to what platform does it run on. We have a day-long class. There's actually depending on which one you sign up for, a 2 to 4 hour tutorial. We taught one at SC09 last year. We put in for one at SC10 this year, so people go to supercomputing, please sign up for the course if you're interested. Let's see. So it's a pretty vibrant project. We have over 50 person-years of effort. It's over 1 million lines of code. It's a big player, and let's see, the Office of Science, the Office of Nuclear Energy, the NNSA. The next generation of the NSF TeraGrid is going to be called XD, and so we have emerging relationships with those XD centers. And so there are a lot of people working on this product. I think we have about the equivalent of 12 FTEs a year doing development. We have 30 developers who have write access, but not all those people do development every day, of course. Okay, and so then recently we went out and showed good scalability at pretty large scale. So we got some, I think, quite large supercomputing allocations at machines across the country, and looked at data set sizes that range from 1 to 4 trillion cells to 10 KQ, and we're able to show that we're able to process data, at that scale. And so this is kind of the next generation of data, but we're pleased to show that we were able to process that next generation. So the barrier for adopting a new Viz tool is always how to get your data into the Viz tool and get going. And so there are really 2 ways to do that. The first way is to write to a format that Viz is familiar with. And we have 100 readers. People tend to gravitate towards the VTK and silo readers. Another way is if you have a file format already, you can write a plug-in file format reader for Visit. My guess is you use the one that Ray Graph wrote. And so I gave this talk once and someone said, how long did it take to write a reader? And amazingly, I said, it took me a half hour. And I thought, wow, that's fantastic. So it's not too bad to write a plug-in file format reader. I don't think anyone's going to beat Ray's record, but that's still pretty good. The third one is a very heavyweight solution. I put it up here just to mention that it's possible. You can integrate Visit in situ. So there's a live Visit you can link into your simulation code and bypass I/O altogether and do code knowledge. Okay, so Visit, what's the big deal? Everything works at scale. The algorithms were all designed to work in distributed linear parallel setting. It's a robust, usable tool, and we're worried about Viz experts who want to make movies. We're worried about code developers who want to debug their codes. And we're worried about people that want to gain scientific insights. So we have a lot of use cases in mind. If you want to learn more, Google not Visit, but Visit Visualization. Here are some websites, the users list. I already mentioned that we'll hopefully have a tutorial of SC10. The code's available via Subversion or also through the website, and that's how to get a hold of it. So thank you for your time. Thanks for inviting me.
Thanks a lot. There's a couple of questions.
Can you do spherical coordinates?
What's that?
Can you deal with spherical coordinates?
Yeah. So I could just say yes. Let me dig one level deeper. So often we try to handle that at the reader level, and so we want things to show up in the X, Y, Z space. That makes sense to us. When we get data that's our data feed, we have transformations that we can apply so that it will show up in spherical coordinates. When you do your picks, really the issue is you want it to show up as as a sphere, and you want when you pick for it to be that you actually get an arc theta feed coordinate to go with it. And so
but you're saying you're doing it as if embedded in an XYZ space.
Well, so correct. So so the question is, what do you want, right? My thinking is you actually want to see it as XYZ on the screen, but you want to give it to us as arc theta feed.
Not really. I'm doing, for example, simulation on the surface of a sphere. So I actually want to see, for example, orthographic projections of that. So you can spin with such things, or I have to write my own code somewhere.
Yeah. So that shouldn't be a problem. So what I just heard is that you'd actually like to see, if it were a climate simulation, flat, long elevation, and you'd like it to be the unrolled sphere, so to speak. You'd like yeah. Well, let me say this. I think we support both, and both pretty.
And do you think 8GF5?
Can we can continue this discussion a little bit later and see if there's some other questions. Someone?
Yeah, regarding the movies, can you have a movie with like around the ring around the trajectory? You define that and then you run for the ring?
So exactly. So there are a couple ways to do it. We have keyframing mode. I personally don't like the keyframing mode. With the keyframing mode, you can set up various views and tell them to interpolate between views with the keyframe. I personally like to use the scripting language because I have a lot more control. And so you can set up, again, peg points and then have a bit of spline between those peg points. So there's definitely functionality. So I guess I should mention, if you go to this visitusers.org, I put it at the screen as you can see what I'm pointing at. If you go to visitusers.org, there's on the front page there's something like a tutorial, and that's one of the examples in the tutorial is how to make the camera fly around.
Okay, I have one question about, let's say that nowadays experiments produce a lot of data, 3D PIV in time or something like that. Is that something that could be handled by these types of tools, or would there be a need for that?
I think there definitely is a need for that. I think you're exactly right. So our niche is big data, and experimental data is getting bigger and bigger. And so we have some success stories with experimental data. I didn't focus on it in this talk, but I think that definitely fits within what we're trying to do with the project.
Okay.
I don't know whether you can answer this question, but we recently made a transition from OpenDX to ParaView, sort of also to exploit the parallelism that is provided by ParaView. So what would you say, what are the key differences between Visit and ParaView? As I understand, the underlying toolkit is...
No, that's right. Yes, we both use VTK. We actually own our parallelization model, and ParaView uses the VTK parallelization model. I'm trying to find a diplomatic way to say this.
You're in good company.
So we put a lot of effort into making the code scale up to the largest data sets. And we've had a lot of people come on board with our project recently, and all those folks have said, wow, we tried using ParaView and we couldn't scale up to our biggest data sets. And so I think that we have put a lot of effort into demonstrating scalability. We've published in that space. We've talked about our results. And the ParaView team, we have very similar underlying architectures, and I think they can get there, but I think they haven't done the work yet to actually be able to scale up to the biggest data sets.
Okay, so let's thank you.
Thank you.
So the last item on the list here is the summing up enclosure, and we have Henrik and Philip to take care of that.
Say anything?
No. I just want to sum up. First of all, I would thank you all for coming here. You have been here for 4 weeks, hectic 4 weeks, and a lot of interesting stuff, etc. I counted on the talk that were given here today, and it was about the 20 people outside of the age who yesterday and today, and then I counted so that at least a dozen of the people we have previously been cooperating with writing papers together. So now I hope that also the rest that are left will do that in the future. And Jonathan Morrison, who left now, he asked me, I think one of the first days, he said something like, what do you expect us to do and what is the outcome of that? And then I said, I will be happy if you are happy. Not as happy, of course, but that you actually are happy because you did something. And then so I hope you find you are happy and that you actually got something out of this. And let me, let me cite Churchill. So then I should cite Churchill and say, now, this is not it. It is not even the beginning of it, but maybe it's the end of the beginning of a very successful collaboration. So with this, I hope, thank you all for coming here, and I hope you all have a safe trip back home, and we'll meet again soon.
Can we answer questions?
There's no chair for this session.
Yes, go ahead. Yes, please.
Was there a question?
Go ahead.
say maybe a couple of things. What struck me in the last 2 days is, among many things, how much computational the effort has become in recent years, and how little innovations have come into experiments. I think this seems to be an issue. Maybe experiments in terms of facilities have been extraordinarily advancing, but experiments in terms of tools for measurement, maybe they haven't gone along as far. And more quantitatively, what I was impressed by was the conclusions you drew yesterday on this ICET comparison thing. What you showed us was a probe resolution of 20 and probe resolution of 40 volumes made already significant difference. I think that was a very important lesson, I would say, and maybe something we should keep in mind for future measurements which use hard wires. Maybe we should be much more careful than we were before. And I also felt that some of the results you had, you can create models. You know, you can say you have a certain spectral shape, like Lingard did some time ago, but maybe you can do more sophisticated data. But actually, quantitatively assess how the resolution effects that you have, because it will impact the measurement. I think it would be nice if you and your collaborators would write up these discussions and results in some open literature, so it will serve as a guidance for younger people who can get into the field. That was very nice.
Yeah, thank you for that comment. And actually, this is on its way together with ICET collaborations. These will come out. It will take some time, but hopefully there will be something quite useful within this year at least.
Another thing we haven't discussed, but Philippe made a set of remarks yesterday which I thought were very important. We don't seem to question the resolution of the DNS as much as we should. Really, especially when we get down to the wall, even to say a homograph scale is enough or equivalently nu or u star is enough is actually not necessarily good. Sometimes DNS people may not appreciate such remarks, but I think it's really very important for us to keep in mind that resolution is not just a matter of experimental problem, but also of DNS.
No, and I think the talk by Philippe yesterday was really appreciated by the experimentalists, maybe more than by the Americans. Maybe. But another thing, I completely agree with you, because I have said this for a long time. For instance, even the mean velocity, when we measure the mean velocity, what we principally do is take the sort of the probability density distribution and take the average, get the average from that. And if we cannot measure the probability density distribution correctly, we are not, that will surely show up in the RMS, the higher moment, but it will also, in some sense, also show up in the mean. So we cannot even trust the mean if we cannot measure the fluctuations correctly. It may not be such a large effect, but we have seen some effects at least close to this.
Can I just add something just to what you said? I don't think it's just hot wires. I think LDV, spatial resolution. I think DIV has issues. PIV, outer plane components, PIV near walls, and so forth. So I think there are challenges across the frontier, and they haven't been really dealt with as one would have hoped over the last 10, 20 years.
Usually, the way to calculate a small scale is through the homograph relation. L over eta is Reynolds number to the power minus 3/4 or whatever, 3/4, or the equivalent version of it near the wall. But because of this extraordinary intermittency that increases with Reynolds number, Victor Yacob and I calculated, and we found that it's not any longer possible to use that simple relation. Depending upon the accuracy to which you want to go, your power will actually go up. It's not Reynolds number to the peak orders. It may very well be as bad as Reynolds number to the power 1, in which case your resolution requirements will go up as you go up in Reynolds number. So if that is the case, I think we are up against a bigger battle than we thought we were.
Okay. Any other comments or questions?
I think we should give a hand of
Yeah.
thanks to everybody who made this possible. And they should just not clap themselves and just stand and enjoy it.
Okay, so with this, I guess we end the beginning.